thank you for inviting me to give this talk. So I am a PhD student in Grenoble in France, where I work with Henri-Claude Nataf in Grenoble and Stéphane Labrosse in Lyon. This PhD is part of the Reverse Research Grant led by Nathanael Schaeffer. And to obtain some of the results that I will show in the next slides, we collaborated with Nicolas Coltis at the University of Nice in France and Nicolas Flamand at the University of Wollongong in Australia. And so I will talk about the coupling between mantle convection models and geodynamo models. So inside the Earth, there are two convective systems which transport heat from the inside to the outside of the Earth. The closest to the surface is the mantle, mostly made of solid silicate. And below this mantle lies the outer core, mostly made of liquid iron. Those two systems interact at the core-mantle boundary, the CMB, with chemical and thermal interactions that are very asymmetrical, because the mantle has a very large viscosity, with typical velocities in the mantle of the order of 1 to 10 centimeters per year, while the liquid iron in the core has a much smaller viscosity, with typical velocities of the order of 10 kilometers per year in the core, which means that thermal heterogeneities at the top of the core are quickly equilibrated, while thermal heterogeneities in the lower mantle can last a long time compared to the timescales of core dynamics. And for this reason, the mantle sees the core as a fixed temperature condition at the CMB, while the core sees the mantle as a fixed heat flux condition at the CMB. Mantle convection controls both the average value of this heat flux and the spatial distribution of the heat flux. This mantle convection, CMB heat flux, is expected to be heterogeneous, with hotter regions in the lower mantle typically below large low velocity provinces, and colder regions typically below subducting slabs. The hot regions translate into a lower heat flux, which, if low enough, can imply a stratification at the top of the core, while the colder regions translate into a higher heat flux, which would enhance locally convection in the core. Those effects add up to the main source of convection in the outer core, which is the flux of light element coming from the inner core crystallization. So we can have information regarding the present-day CMB flux using a seismic tomography, and we can notably tell that the temperatures in the lower mantle are heterogeneous at the present day. But we can also use mantle convection models, notably to constrain the path of the CMB flux using plate-driven mantle convection models. And important results from these models, notably, are that heat flux heterogeneities can be large and they can fluctuate over time. So to sum up, CMB heat flux heterogeneities at the CMB exist at the present day. They can be large, and we should expect them to have been fluctuating over the geological times. So because we know that heat flux heterogeneities should exist at the CMB, we can try to see the effect it has on the geodynamo. A first way to do that is to apply a heat flux pattern at the top of the core in dynamo models. And it has been done as soon as the first geodynamo models have been available by Glassmeyer and collaborators. This figure is taken from their study. It shows the magnetic pole trajectory for different heat flux conditions. And you can see that the stability of the magnetic dipole largely depends on the heat flux conditions. Those studies, usually they find that polar cooling of the core tends to stabilize the magnetic dipole, like in this case, while an equatorial cooling of the core tends to destabilize the magnetic dipole, like in this case. Another possibility is to look at the paleomagnetic record and the geological record and try to find correlations. One of the well-known paleomagnetic data we have access to is the polarity of the magnetic field. We know that the Earth's magnetic field reversed its polarity through the geological times with a reversal frequency that has been varying. And some correlations have been proposed, like here by Petrilis and collaborators, between the reversal frequency in black and in blue, the amount of equatorial symmetry in the continent distribution, or here by Begin and collaborators, between the reversal frequency and the number of large igneous provinces in the mantle. The idea behind these correlations is that mantle convection features like plate tectonics, mantle plumes, or true polar wonder could modify the CMB flux, which would affect the reversal frequency. So our goal is to try to understand how these heat flux heterogeneities affect realistic geodynamo models, and we are notably interested to find a link between reversal frequency and mantle convection. For that, we want to obtain more realistic CMB flux heterogeneities, and we want to go towards more realistic geodynamo simulations. So we are using numerical tools. For that, we have access to two 3D mantle convection models that have already been published before this PhD. One of them is fully self-consistent, and the other one is driven by a plate reconstruction. And we also use geodynamo numerical models using the eggshells code to run low viscosity dynamo models with heterogeneous heat flux conditions at the CMB. So I will first talk a bit about mantle and core dynamics and how we can couple both together. So in both systems, we are interested in simulating thermochemical convection in a rotating spherical shell with similar aspect ratios, but there are also large differences between these two systems. In the case of the mantle, there is a complex rheology with a viscosity that depends notably on the temperature, the composition or the deformation rate, for instance, while the core can be modeled with a constant viscosity. Inertia is negligible in the mantle, while the core is highly turbulent. The mantle is made of an electrically insulating material, while the core is conducting, and there is a dynamo effect. And finally, the effect of rotation is negligible in mantle dynamics, while it has a strong effect in core dynamics. So to couple both systems, ideally, we would like to simulate both together with a mantle convection that would control a time-dependent CMB flux and a core convection that would respond to its time-dependent forcing, with potentially also a growing inner core. But this is not tractable numerically due to the different timescales between these two systems, notably. So instead, what we do is to take advantage of this timescale separation between the mantle and the core. And we first simulate mantle convection for typically 1 billion years. From these mantle convection models, we select snapshots, or we do statistical analysis of the CMB flux. And we simulate the geodynamo with fixed CMB flux conditions that are instantaneous with respect to mantle convection. So I will first describe how we obtain these realistic CMB flux conditions using mantle convection models. So we want these models to share some characteristics. We want them to reproduce a long enough time series of mantle convection, typically more than a supercontinent cycle. We want them to include chemical piles at the base of the mantle, which are important because they impose a low heat flux below them. We want the models to have realistic parameters, and we want them to be related to plate tectonics. And for that, as I said, we have two different models. One of them is producing plate tectonics self-consistently without being forced at the surface. I will call it the MC model in the following. And the other one is driven at the surface by a plate reconstruction. I will call it the MF model in the following. Because we want to relate mantle convection with core dynamics, we have to express the output of the mantle convection model in the correct reference frame. And for that, we have to consider true polar wonder. So because of mantle convection, masses are reorganized inside the mantle, which modifies the inertia tensor of the Earth. And the maximum inertia axis tends to align with the rotation axis, which implies a rotation of the Earth with respect to its rotation axis. This is what is called the true polar wonder. And the maximum inertia axis in mantle convection model can be obtained from the degree 2 of the geoid. So if the model is self-consistent, the procedure to correct for this true polar wonder is to extract the geoid from the model. From this geoid, compute the maximum inertia axis, and then rotate the outputs to ensure that the maximum inertia axis stays parallel to the rotation axis. Which means that in these self-consistent models, the degree 2 of the geoid is the only constraint on the reference frame. It is a bit more complicated for plate-driven models. For these models, we can also use this geoid-based correction, but the geoid can be inconsistent with paleomagnetic constraints, which means that the maximum inertia axis predicted by the geoid can potentially not be aligned with the magnetic dipole. So for these models, it is also possible to use the magnetic dipole as a constraint on the reference frame. So after true polar wonder correction from the two mantle convection models, we end up with 6 different cases. From the MC model, we have 2 different cases that both reproduces 831 billion years of mantle convection in a self-consistent model. MC0 is not true polar wonder corrected, so it is expressed in the initial simulation frame. MC1 is true polar wonder corrected using the geoid, so it is expressed in the reference frame of the inertial axis. To explain a bit more how this correction works, we first extract the geoid from the model, and we keep only the degree 2 of the geoid. From this degree 2, we can compute the maximum inertial axis that I show here with this white star. And we rotate the outputs to ensure that the maximum inertial axis stays parallel to the rotation axis, which brings the positive anomaly of the degree 2 geoid towards the equator. We also do this correction for the NF model, which reproduces 1 billion years of mantle convection driven by a plate reconstruction. So MF0 is not true polar wonder corrected, so it is expressed in the non-net lithospheric rotation reference frame of the initial model. MF1 is true polar wonder corrected using the geoid. MF2 is also true polar wonder corrected using the geoid, but a slightly different geoid in which the lateral viscosity variation have been removed in the upper mantle. And we also have an alternative case, MF star, in which we rotate the outputs in the Paleomagnetic reference frame. To explain also a bit more how this correction works, we take the output of the NF model in the non-net rotation reference frame, and we rotate the surface to ensure that the magnetic dipole is aligned with the rotation axis, which means that the continents have the correct paleo latitudes, and we apply the same rotation to the CMB flux. So here I will show how true polar wonder affects the large scales of the CMB flux. So we computed the circular harmonic decomposition of the CMB flux, and I will show the time evolution of the degree 1 and degree 2 circular harmonic coefficient for the MC0 case before true polar wonder correction and the MC1 case after true polar wonder correction. And from this figure, you can see the three main effects that true polar wonder has on the CMB flux. First, it affects the hierarchy of circular harmonic coefficients. You can see that for MC0 at minus 300 million years, for instance, this is the degree 2 order 1 coefficient that dominates, while it is the degree 2 order 0 coefficient that dominates in MC1. It can change the sign of some circular harmonic coefficients. This is the case of the degree 2 order 0 and the degree 1 order 0 coefficients between MC0 and MC1. And it introduces fast time variations that you can see here or here, for instance, which are not visible if we, before we do the true polar wonder correction. Importantly, in this model, there is a strong degree 2 order 0 component with a change of sign between the MC0 and MC1 case, which is important for the geodynamo potentially, because with a positive degree 2 order 0 coefficient in MC0, it means that the core is mostly cooled at the poles, while with a negative coefficient for MC1, the core is mostly cooled at the equator. Here I show the same figures, but for the cases derived from the MF model. So I won't enter into the details, but you can see the same three main effects here. You can notably see that for MF1, there are faster oscillations, which are due to fast time variations in the geoid caused by the update of the plate reconstruction at the surface of the model every 1 billion years. These fast variations are not visible in MF2 because we removed the lateral viscosity variations to compute the geoid. And in MF star, you can see that there is a sharp change of sign of the degree 2 order 0 coefficient, which could be important potentially for the dynamo. And finally, we computed a principal component analysis of the CMB flux to extract the dominant patterns. So this PCA decomposes the CMB flux into a sum of components with a time-dependent weight, a singular value, and a pattern. Those components are perturbation to the average heat flux, the average pattern. In this figure, I give for the MC0 and MC1 cases, the average heat flux pattern at the top and the three more dominant components at the bottom. And here I give the amplitudes of these three components for MC0 and MC1. You can see that for the true polar wonder corrected case, there are faster oscillations due to the true polar wonder. So this analysis, it enables to obtain the dominant patterns of the CMB flux. Those patterns mostly reflect the positions of the conical piles, especially the average heat flux patterns here. It gives complex patterns that are representative of the full simulation, but the downside is that they are difficult to interpret, these patterns, notably in terms of their relation to plate tectonics. So that's all about the mantle convection and the CM flux. If you want more details about the effect of true polar wonder on the CM flux, we have an article that has just been accepted in Solid Earth. So now I will talk about the geodynamo simulations. So for these simulations, we use a codensity approach by combining the temperature and composition light element into a single variable. For the boundary condition, we use conducting inner core for most of the simulations and an insulating inner core for the most numerically demanding simulations. We use an insulating mantle and a no-slip condition at both boundaries, and we fix the codensity flux at both boundaries. At the outer boundary, the codensity flux is decomposed into a mean flux, which is set to the isentropic flux, and an heterogeneous part with an amplitude and a pattern. And because we use the Boussinesq approximation, this mean flux is actually equals to 0. So those are the equations that are solved by eggshells in the Boussinesq approximation and non-dimensionalized. So the Navier-Stokes equation, the induction equation, the conservation of the codensity, and the null divergences of the velocity and magnetic fields. The non-dimensional parameters are given here: the Rayleigh number, Ekman number, magnetic Prandtl number, and the Prandtl number. And here I show some outputs that I will be discussing in the next slides. EU is the kinetic energy integrated over the whole volume. EB is the magnetic energy integrated over the whole volume. Rm is the magnetic Reynolds number, which quantifies the strength of the flow. Lambda is the Elsasser number, which quantifies the strength of the magnetic field. And I will quantify the dipolar fraction at the CMB in two different ways. This first definition is using the radial part of the magnetic field at the CMB and all the circular harmonic degrees. And to compare with the values we have for the Earth, I will also use this second definition, in which I use the full magnetic field at the CMB and only the degrees lower than 13. So here are the large scales heat flux pattern that we apply at the top of the core. In red, the heat flux is positive and the core is cooled. In blue, the heat flux is negative and the core is heated. So Y10 is a north-south asymmetry in the heat flux. Y11 is an east-west asymmetry. Plus Y20 is a polar cooling. Minus Y20 is an equatorial cooling of the core. And Y22 is a two antipodal heat flux highs surrounded by two antipodal heat flux lows. We also use more complex patterns that are extracted from the mantle convection models that I showed previously. So GMC1 is the average heat flux pattern in the MC1 case. GMF1 is the average heat flux pattern in the MF1 case. T0 MF0 is the pattern at the present day in the MF0 case. And T450 MF0 is the pattern at 450 million years ago in the MF0 case. And I will quantify the amplitudes of these patterns by normalizing it with the inner boundary flux. So here I show the reference dynamo cases without heat flux heterogeneities that we use. This table gives the non-dimensional parameters of these dynamos. And on this figure, I show the Ekman number and the magnetic Prandtl number of these dynamos compared to some previous studies that also studied the effect of heterogeneous heat flux at the top of the core. You can see that this case here with an Ekman number of 10 to the minus 4 is standard compared to what has been done previously. Those three cases at an Ekman number of 10 to the minus 5 are at the boundary of what has been done previously in terms of Ekman number. And this case with an Ekman number of 10 to the minus 6 and the magnetic Prandtl number of 0.2 is getting closer to the parameter regime of the Earth, which would be at around an Ekman number of 10 to the minus 15 and a magnetic Prandtl number of 10 to the minus 6. On these two figures, I compare some outputs of these reference cases with the values we expect for the Earth. This figure gives the average value of the dipolar fraction and the ratio of magnetic to kinetic energy. And this one gives the Elsasser number and the magnetic Reynolds number. The expected values for the Earth are shown with the blue range and the red range. You can notably see that all of our dynamo cases have a ratio of magnitude to kinetic energy that is much too low compared to the expectations for the Earth. But we still have two cases that have a ratio of magnitude to kinetic energy larger than 10. And for this reason, I will call those two cases SF for strong field. Those two strong field dynamos here and here have a magnetic Reynolds number that is either too low or just at the limit of what we expect for the Earth, while the three others have a high enough magnetic Reynolds number. And for this reason, I will call those three cases HRM for a high magnetic Reynolds. So here I will show how the large-scale heat flux pattern affect the behavior of the most standard case at an Ekman number of 10 to the minus 4. I will show the average value of the magnetic Reynolds number and the Alsacer number as a function of the amplitude of the patterns. And the color corresponds to the different patterns. The white dot is the simulation without heat flux heterogeneities. And you can notably see that the plus y20 pattern in green, it decreases the strength of the flow and increases the strength of the magnetic field, while the minus y20 pattern in red and the y10 pattern in blue, they both increases the strength of the flow and decrease the strength of the magnetic field. It is notably interesting that the y20 pattern has an opposite effect depending on the sign. So here I show a bit more in detail the results for this y20 pattern. I show the dipolar and the probability distribution, of the dipolar fraction, the ratio of magnitude to kinetic energy, and of the dipole latitude as a function of the amplitude of the y20 pattern. So on the right, the amplitude is positive, it is a polar cooling, and on the left, the amplitude is negative, so it is an equatorial cooling. The color of the probability distributions gives the behavior of the dynamo. In blue, the dynamo is dipolar stable, so without reversals. In green, the dynamo is dipolar reversing, so with reversals. And in orange, the dynamo is multipolar. The range in red gives the expected amplitudes for the y20 pattern from the mantle convection models. And the gray range gives the expected amplitude for a complex pattern, also from the mantle convection models. So you can see that the plus y20 pattern tends to increase the magnetic energy, and there are no reversals in this case, while the minus y20 pattern implies a fast transition towards multipolar behavior for amplitudes that are within what we expect for the Earth. Here I will show the same results, but for the 5 different dynamo cases. So the probability distributions of the dipolar fraction on the left and the ratio of magnitude to kinetic energy on the right. For the y20 pattern, so polar cooling on the right, equatorial cooling on the left. I will first show the 3 high magnetic Reynolds cases. The first one here at an Ekman number of 10 to the minus 4 is the one that I just showed previously. And you can see that the 2 others high Reynolds cases behave similarly. The plus y20 pattern tends to increase the magnetic energy, while the minus y20 pattern implies a fast transition towards a multipolar behavior. The 2 strong field cases are here at the bottom, and the behavior is a bit different for those 2 cases. The plus y20 pattern slightly decreases the magnetic energy, while the minus y20 pattern implies a much less abrupt transition towards multipolar dynamos. In the SF1 case, we still obtain a multipolar dynamo for amplitudes that are much larger than what we expect for the Earth, while for the SF2 case, we don't even obtain any multipolar dynamos. So those results were for a simple large-scale pattern, but we are also interested in the effect of more complex patterns. So we also applied the complex patterns that I showed previously to the most standard case, again, the 10 to the minus 4, the Ekman number of 10 to the minus 4. This figure gives the fraction of spherical harmonic power of the y10, y11, y20, and y22 components within these complex patterns. You can notably see that the GMC1 pattern in blue is the only one with a strong Y20 component, which is not the case for the others. And in these figures, I give the average value of the dipolar fraction as a function of the amplitude of the different patterns. The color of the dots gives the sign of the Y20 component within these patterns. In blue, the Y20 component is negative. In red, the Y20 component is positive. So if the effect of the Y20 component within this complex pattern were dominant, we would only obtain dipolar dynamos in red and multipolar dynamos in blue. And you can see that it seems to be the case for GMC1, but it is not the case for all the others, which means that if the Y20 component is strong in the complex pattern, it seems to control the behavior of the dynamo. But we have a loss of the stabilizing effect for the positive Y20 component if the Y20 component in the complex pattern is not strong enough. And finally, the dotted lines for each case gives the actual amplitude for each pattern in the mantle convection models. And you can see that for these amplitudes, the dynamo tends to be multipolar here, here, and here. There is only the GMF1 pattern that imposes a dipolar dynamo at the amplitude predicted from the mantle convection model. So to conclude, we tried to couple core and mantle dynamics by using mantle convection model and rotating the outputs in the correct reference frame for the core. From these mantle convection models, we extract snapshots or we do statistical analysis of the C-ambit flux, and we apply fixed C-ambit flux conditions in geodynamo models. We find that the true polar wonder can change the hierarchy and the sign of circular harmonic coefficients of the C-ambit flux. The variations can occur on timescales that are shorter than the usual convective timescales. And importantly, it can notably redistribute the C-ambit flux between the equator and the poles. And finally, for the effect of heterogeneous heat flux pattern on dynamo models, we find that plus Y20 pattern tends to stabilize the magnetic dipole, while minus Y20 and Y10 pattern tends to destabilize the dipole. The effect is stronger when the magnetic Reynolds number is high and the ratio of magnetic to kinetic energy is not too high. And for more complex patterns, it tends to destabilize the magnetic dipole, except if the Y20 component is strong and positive. And that's all for me. Thank you.